Yeah, the countdown. Well, let's get started. On Friday, you'll be submitting your 2 printed maps that show your design for the network. And remember to include annotations of how much water is being taken out of each junction, the pipe sizes, the flow rate through the pipe, pressure at the junction, and so forth. Yeah.
Another question, why, if you display the flow rate at the junction, is it that it shows 0?
Well, there are different, lots of different categories that you can annotate. What you need to find is the demand collection. There's different ways of specifying the demand. And so it's just a different category that you need to annotate. Then on Monday, homework 8 will be due. Remember that that's all basically related to Manning's equation and different solutions of that. Since our class last time, I posted the recording that Dr. Pearson made of how to use your calculator for solving the trapezoidal channel Manning's equation problem. And that's something that's going to come up repeatedly through the semester, and I'm going to assume in an exam, for example, that you can solve for the normal depth and the trapezoidal channel. And so you need to make that assumption true. If you don't already know how to use your calculator to solve equations, then now's the perfect time. It's a very useful function to be familiar with. So if you don't have a Casio calculator, I understand that they're very cheap and available at Walmart. So if you buy an HP, I'll help you figure it out. But that's the only one I know how to use. We're going to talk more about channel efficiency today and tackle the complex case of a partially full circular pipe. So one of the issues that sometimes comes up when very large flows are encountered in a stream is that the main channel will have one roughness and that the floodplain will have another. And so this is a cross-section that's showing a typical trapezoidal channel here with 2-to-1 side slopes, and it may be that this is just an irrigation canal of some sort. But then you can see as the water level rises and it spills out of this typical flow channel, there is a floodplain that's much wider, and it may be that this part of the channel is lined with grass, weeds, cars, buildings, all sorts of debris that would have a much higher N value than the main channel. And so if you're going to apply Manning's equation to the entire cross-section, there has to be some way to come up with an average N value to account for the average resistance that's encountered by the cross-section. Now, the more sophisticated approach is actually to solve Manning's equation not as a whole cross-section based on some average N value, but it's rather to break the channel into pieces and solve for the flow of the individual pieces. And there are software programs that enable that to be done fairly easily. But if you're just going to apply Manning's equation to the cross-section as a whole, one of the many different ways to find an average N value is the Horton-Einstein method. And I've just brought it up on screen there. And you can see that what it is it's a weighted approach that takes into account the perimeter of any element relative to the total perimeter. And so rather than being area weighted, which is what we often do in situations like this, it's perimeter weighted. And so what that means is that, let's say section 1 is made out of grass, we'd find the length of that section, multiply it by the N value to the 3/2 power, add it to the length of this section, multiplied by the N value for that section to the 3/2 power. And through the process of just accumulating the perimeter times the N value to the 3/2 power for each one of these, and then dividing by the perimeter, taking it to the 2/3 power, that's an approach that empirically has been shown to, with relative accuracy, be able to represent the overall effect of the roughness. And so a section that is very, very long and is going to impart a lot of resistance because of its length gets accounted for and weighted more than a section that may be shorter. So composite roughness is one of the things you'll have to do when the flow levels get very high. And by the way, there's a term that's sometimes called a channel forming flow. And ordinarily in a natural channel, the flow that comes through every 2 years approximately is the flow that would fill the natural embankment to capacity. And last time we got together, we took a look at a channel that's in pretty bad shape. Let's see if we can find that image. Where is that? Here it is. Okay, so this is a channel that's suffering from scour because the flows that come through were larger than they used to be, and the situation isn't stable. But you can sort of get a sense that this seems to be the channel nowadays. And so a flow that's a result of a rainstorm that would come every 2 years on average, that would be its average return period. Ordinarily, a channel is formed by a flow that has a 2-year return period, and then the larger flow rates that come through less often would escape that main channel and would be accommodated by the floodplain. Okay, back to here. All right, so channel forming flow is a term you may hear in the future, especially if you take hydrology. In previous examples, I've shown you that sometimes it's more convenient, instead of calculating the hydraulic radius and taking that hydraulic radius to the 2/3 power, that if you're solving for normal depth y, normal depth is going to be one of the parameters that's both in the area and the wetted perimeter. And so just taking the area to the 5/3 power and keeping the perimeter separate from that can be a simpler way to find the normal depth. And so we've seen this substitution before, but for a fixed end value, meaning that we can't monkey around with the material that a channel is made out of, and if the slope is fixed, then how do you maximize the flow rate? So you only have control over geometry. And so, of course, the way to maximize flow rate is to find the channel that's most efficient. And we've looked at this before, the idea of how might a channel that's very narrow and tall impart resistance to the water flowing through it compared to a channel that has the same cross-sectional area but is a little bit less extremely shaped in an extreme way. And remember, what was the issue that imparts more resistance to flow? What would make it so that less flow can be accommodated through this channel than through a more rectangular, squarish channel instead? Right. It's maximizing the surface contact. The resistance is imparted by the solid, and so if there's more wetted perimeter, as there is here, then a more efficient channel, there will be lower flow. And so let's take a look at a spreadsheet example that illustrates this effect. Okay, so we have a rectangular channel, and we'll have varying bottom widths, varying depths, some area, a wetted perimeter from that, hydraulic radius, and the flow rate in terms of cubic meters per second. All of these are going to have the same end value, and all of them are going to have the same slope. And so if we refresh our memory what the geometry of these is, there's one where the bottom width is 2, one where the bottom width is 10, one with the bottom width of 5, and the bottom width of 4. These all have the same area, and so the depth of flow is 10, 2, 4, and 5. Area is just going to be the flow depth times the bottom width. Okay, since it's rectangular, it makes it easy to calculate the wetted perimeter. It'll just be the bottom width plus 2 times the flow depth to calculate the wetted perimeter. It would be trickier if it was a trapezoidal channel, but it's not. Hydraulic radius is area divided by wetted perimeter. And so now to find the flow rate using Manning's equation, we say, let's paste that in. Oh, we don't want to edit it though. It's thinking. It's not responding. There it goes. All right. Area to the 5/3 power. Slope to the 1/2 power. N value. And the wetted perimeter to the 2/3 power. And I need to anchor a few of these cells so that when I drag it downward, it isn't going to lose its perspective. Okay, so flow rate capacity of 144 cubic meters per second. And then if we drag that down, it seems like the most efficient of them would be this 5x4. Now, the most efficient overall, we might actually be able to get a little bit more capacity out of that. That's just the most efficient of the sections that we took a look at. But the question is, what's the most efficient section that's possible? So could we squeeze a little bit more capacity out of a channel that's 20 square meters in area?
There's some relation to the second and fourth one being the same, having to do with like working with each other.
So why, you're asking why do these have the same flow capacity?
Yeah, that's-
Because they've got the same wetted perimeter. Yeah, it's the same 14 meters of wetted perimeter, either shape. They have the same slope, same N value, the same area, the same wetted perimeter, and so even though they look startlingly different, they hydraulically have the same capacity to carry flow.
Those aren't the same values that were on the Excel sheet.
No?
I mean, they're readable on Excel, but they're not the.
Yeah, I wonder if I put some values in wrong here. It's the same as I got in my spreadsheet. I wonder if I used a different N value in this experiment. No, 1%. Well, I might have some errors just in these values that have popped up on screen here. Let's double check. Okay, so the flow rate of the area to the 5/3, we'll use this one. It was our most efficient. So 20 square meters, 5/3 power, and we've got the slope 0.01 to the 1/2 power, the N value 0.013, and then the perimeter to the 2/3. And the perimeter of this one is going to be 8 plus 5 is 13 meters, the 2/3. All right. Can you guys solve that with your calculator, and we'll find out what the capacity is and find out whether the spreadsheet is correct or whether these values that I've got hidden here, I might have typed in some wrong values based on the spreadsheet. The spreadsheet's right. Always trust the spreadsheet. All right. I'll just edit these to match the spreadsheet. I think what I did is I probably edited the example and then didn't change the values. So thank you for noticing that. 195. This was 205. And 195. All right. So these two channels are equal to each other in terms of capacity, but they have very different, look cross-sectionally. And so, if you're actually going to have to choose between one of these cross-sections, you may ask yourself, what's more expensive, the right-of-way to purchase land so that you don't have to excavate as deep, or is it more expensive to excavate deeper and then have less of a right-of-way if this channel is meandering through, let's say, an industrial area, if it's an irrigation canal or a drainage canal of some sort? The most efficient section is a half square. And so the best we can do is, if the area is still 20, so most efficient, is a half square. So still with a cross-sectional area of 20 meters, then the area will be y times 2y for it to be half a square. We have half, the square, cut it in half, then area is 2y squared, so y is 3.1623 meters. And let's try that in the spreadsheet to see what sort of a flow rate we can get with that geometry. Okay. So what if the B was 3.1623 and the area is 20, and so, I'm sorry, that was the y. Okay, so the B will be area divided by y. So that would give us a bottom width of 6.32. Okay, the wetted perimeter has been minimized. Hydraulic radius and our capacity 208.8. And so that's the maximum capacity that could be accommodated for a channel on this slope with a roughness value of 0.013 and it being a rectangular section with that area. So the most efficient rectangular section is a half square. Here's the best trapezoidal channel. It has a specific side slope, and it's a relatively steep side slope, actually. Remember that M in this is referring to the horizontal component relative to a vertical component of 1 for the side slopes. And so square root of 3 divided by 3 is going to give a pretty steep side slope, a side slope that could really only be accommodated with concrete or maybe a stone lining. You couldn't have a natural earth-lined or grass-lined channel maintain a side slope that steep. But for any particular cross-sectional area, this is how you can find the trapezoidal channel that can convey the most flow. And it turns out that it's the trapezoid that would be described by a circle with radius y for a certain depth. Other trapezoids could have a wider B value or a less steep side slopes, but this is the trapezoid that is coincidental with a circle being drawn inside of it. These parameters are found in your book for the best shapes. The other best shapes here, the best triangle is a half square on edge, and you've got the area, the perimeter, and the top width in terms of the whatever depth there is. All right, so for a rectangular channel with an area of 20 square meters, what dimensions will give the greatest flow? That's what we just solved, that 208 cubic meter per second, half square. All right, this is really the heart of today's lecture, and this is a kind of a iconic figure that you would see in the FE review manual, or any sort of hydraulic text is going to have a figure like this that shows how the flow behaves in a pipe when the pipe isn't completely full. And I'm just wondering if this is skipped over a slide here. No. All right. At the top is a table that's showing how to calculate the area of a circular section where the depth isn't all the way to the top of the pipe. Of course, for a circular section where the water is all the way to the top, then the area is simple. It's just pi d squared divided by 4. But what's shown here on the right side of the screen is the fact that y is smaller than d. D is the diameter of the pipe, and y is the flow depth. And so you can see that there's some angle that is measuring from the water surface intersection points with the channel and the center of the pipe. And so some angle measured in radians. If you know that angle in radians, then you can calculate the area, the wetted perimeter, hydraulic radius, top width. And so the way that you find the angle in radians is with this formula, where it's going to include the ratio of the flow depth to the diameter. And so cosine of the -1, the inverse cosine of that, different calculators call it different things. The cosine to the -1 on my calculator is ACOS. ACOS is what the little button says when I want to do the inverse cosine on my calculator. But let's talk about this figure and what it's representing. It has on this lower x-axis the ratio of the flow through the pipe compared to what the flow would be if the pipe was full. And the way that you use that is you'd solve Manning's equation if the pipe was full. First of all, as a first step, you'd say, okay, I've got a 24-inch diameter pipe. So for the diameter that's given, for the slope that's given, for the n value that's given in any particular example, find Q full. If the water was all the way to the very top of the channel, what would be the flow capacity of the pipe? And then once you know that, then you ask the question for the ratio of the depth to the diameter, find chart y-intercept. Okay, so the ratio of water depth to diameter. In our case, it's 9 inches out of 24, and so that's 0.375. So we'd go here and we'd find here's 0.3, here's 0.35, there's 0.375, go over, and on this figure here, now go down, and it would tell us the ratio of the flow rate when it's partially full, Q, to the flow rate when it's completely full. Look up the Q to Q full. And then as a last step, multiply Q to Q full ratio by Q full from step 1. All right. So I'd like you to give these equations a try. In this example, we have a 9-inch depth. It's on a 0.5% slope, and it's a concrete pipe, and so I'll give you the N value. For this example, the N value when the pipe is full is 0.013. And this N value when the pipe is full is what you should use is in this first step. And then we'll talk more about why I why even bother to give this subscript full? Like, what is that relevant for? So go through the process that's outlined here, and as you do that, I'm going to hand back some homework and quizzes. Okay, so are there any questions on this first part where you find what the flow rate would be if the channel was full? You'll notice that I made the substitution of hydraulic radius is just diameter divided by 4. We can make that substitution when the pipe is full. That the hydraulic radius, remember, area divided by wetted perimeter, and if the pipe is full, then it's just diameter divided by 4. And so if the pipe was totally full, this concrete pipe on a 0.5% slope, its capacity would be 16 CFS. But from the curve, we find that when it's 37% depth, it can carry 24% of the capacity. Why do you suppose that it can't carry 37% of the capacity? If it's 37% deep, why can't it just carry 37% of the capacity that it ordinarily would? What do you mean it's not as wide at this depth? So the depth that we've got right here is 9 inches out of, what's that?
It doesn't reach the maximum width of the pipe.
Okay, so it's not reaching the maximum width of the pipe, and why is that?
At that point, it had less ratio of area to contact surface.
Okay, so you're thinking in terms of area to wetted perimeter, and that's good. That's good. So think about when it's really, really shallow, like if it's very shallow, look at how much wetted perimeter it's got. It's got lots of wetted perimeter and very little cross-sectional area. So you'll notice that on the early phases, this chart is very steep because you're getting a lot of depth, but you're not getting much flow relative to that depth because there's so much wetted perimeter. And so it's a non-linear relationship between increasing depth and increasing capacity. So we've got 37% of the full depth, 24% of the capacity, and so we multiply 0.24 by what the capacity would be if the pipe was full. We get 3.85 cubic feet per second. Any questions about this first procedure here? Yes, Rick?
Is that Cartesian y-intercept on the second bullet there?
Find the,
C-A-R-T?
I think I probably meant chart.
Oh, chart. Okay.
Just got all excited and forgot the H.
Okay.
Yeah.
Just wondering.
No, it's the intercept on this chart.
Okay.
Thank you. Other questions?
Why wouldn't
I'm surprised I don't get more questions about my lousy penmanship. Yes.
Why when it's 95% full is the Q greater than the Q full?
Oh, excellent. Excellent question. So what Leland has noticed is that actually you're better off if the pipe isn't full. Look, 100% flow capacity when it's full, but you'd be better off if it wasn't. All of a sudden when it gets more full, okay, so this is the most capacity you could have, but then as it gets deeper, your capacity decreases. Taylor, why do you think that is?
The same reason why if it's shallow, you're not getting a lot of heat. When you're approaching the top of the circle, say your wet perimeter, it's becoming more and more of an issue as you approach the top.
All right, so you're getting, as it gets deeper, you are increasing the cross-sectional area, but you're increasing wetted perimeter even more. The effect of the additional wetted perimeter outweighs the additional area that you've got. So the optimal balance of flow area to wetted perimeter happens at about 90% depth. But then more and more contact with the surface means more resistance, and so I'm glad you asked about that. I'm glad. That's a good question. I guess this is the velocity relative to velocity full, but even for the, I guess it's 95% depth to maximize the flow rate. Okay. Other questions? Now the N value we used here was in this first procedure. The N value we used is the N value if the pipe is full. But the end value that you should use if the pipe isn't full is different from the end value if it is full. And that nomograph that's on screen takes that into account in the chart. That chart, this Q to Q full, is taking into account the ratio of area to wetted perimeter, and it's also taking into account the effective end value. And so I wanted to show you another way besides the chart method of solving the problem is if we find the angle, 2.63 radians, and from that we can find the area, the wetted perimeter, then we can substitute these values into Manning's equation and solve directly without having to use the chart. Except for that, when the pipe is partially full, the end value isn't the same as the end value would be if it was full. And so we still have to go to the chart and look up the n relative to the end value when it's full. And in our case, remember, we've got the y to d is 0.375. And so the question is, what n value should we use? We're going to use n full times some factor. So again, we find this point on the y-axis of the chart where the half of this takes us to 0.35, 0.375, we go over, and now we're looking at this Manning's chart, down, and so the ratio, oh, I'm sorry, up, not down, we got to go up, because up there is, on the top y-axis is where it refers to the n to the n full. And so the factor that we read off of that chart is 1.28. And so what that tells us is that the n value we should use is 0.013 times 1.28. And so the effective n value is 0.01667. No, 664. And so that's actually what we should put into here, 0.01664. Because the pipe is only partially full. And this 0.013, that's the resistance if the pipe was full. In other words, Manning's equation right here doesn't know whether or not the pipe is full. And so we have to account for it one way or the other, whether it is built into the factor that we use as a Q to Q full. You know, this ratio has the relationship of the resistance, whether it's full or not full, or we have to substitute it in there. And so if we take this approach, then the angle method gives 3.75 cubic feet per second. And so comparing that to 3.85, that's about 2% error, 3% error. And considering it's a method where you're looking up values off of a chart, then that's a fine level of agreement. But if we didn't make that change, if we just used the the n value, assuming the pipe was full, so for n equals 0.013, if we forgot and we did the wrong thing, then the Q that we get, it would look like the flow rate was actually 4.80 cubic feet per second. And the difference is that, remember, when we've only got 9 inches of depth, more of the flow is in contact. It's closer to the resistant surface, and so it has an effective end value that's greater than it would be if the pipe was all the way full. Because when the pipe is all the way full, more of the flow area is further away from the resistance surface. And so end value varies as a function of depth. And a chart like this can help us to account for it. So this is the wrong approach. Remember that if you're going to find the angle, and with that get the area and the wetted perimeter, then you need to find a modified end value for that. Okay, so that's it for today. Just remember that when we get together on Friday, you're going to have some maps for me to look at. And then on Monday, a homework assignment. So you'll be busy, as you always are.